Okay, question 6. We have a car of mass 1,500 kilos pulling a trailer of mass 750 up a straight hill of length 800 meters, inclined at an angle of sine 0.08 to the horizontal. The resistance to the motion of the car and the trailer are 400 newtons and 200 newtons. The car and the trailer are connected by a light rigid tow bar. The car and trailer have a speed of 30 meters per second at the bottom of the hill and 20 meters per second at the top of the hill. Use an energy method to find the constant driving force as the car and trailer travel up the hill. Okay, so before we even answer the question, we're going to draw a diagram. So I've drawn my hill and because we're going to consider the car and trailer together, I've just drawn them together for now. So let's put in all the information we know. We know that the trailer and the mass of the car, okay, so we're going to combine them together and we're going to have 1,500 plus 750 G newtons. Okay, that is the force of gravity. And we can also, if we want to, we can just write this as 22500 newtons if we want. Okay, let's consider the other forces. We have to set the direction of motion, or the car's traveling up the hill, so that's nice and easy. Right, why do we set the direction of motion? Because we want to know the direction that the resistances are acting. They always act against the direction of motion. So they have to be going down the hill. And we can combine the two resistances together to give us a total resistance of 600 newtons. And finally, we have some driving force. There must be something pulling the car up the hill, and we can just call that dF for our driving force. Now they say use an energy method to find the constant driving force as the car and trailer travel up the hill. Okay, so an energy method means that we have to use mechanical energy. And so what we can say is the change in mechanical energy is equal to work done. Okay, the total work done by all the forces. And we can see in the direction of motion, right, the forces working are going to be the forces of resistance, okay, and the driving force. We're not interested in the weight component, right? So this force here, due to the weight component, we're not interested in it because we're going to consider that rather as gravitational potential energy. So remember, change in mechanical energy is work done, excluding gravitational or forces, work done by the weight of the vehicle or the object. So what is mechanical energy? It's change in kinetic energy plus change in gravitational potential energy. And that's equal to work done. So let's consider these two components separately. So let's think about the change in kinetic energy. Okay, well, the car's traveling up a hill. It has a starting speed of 20 meters per second and it reduces its speed to 20 meters per second. So if something is going slower, there's going to be a loss in kinetic energy. Okay, so we have 1/2 m for the mass of the vehicle, final velocity squared minus initial velocity squared. That's going to give us our change in kinetic energy. Okay, so here's our change in kinetic energy. And gravitational potential energy, well, the object's traveling up a hill, which means it's vertically going to be higher. So there's going to be an increase in gravitational potential energy. So gravitational potential energy, we can just say is mass times gravitational constant plus the change in the height. Okay, how high, what's the difference in height from where it started? Okay, and remember that's vertical height, not slant height. So we have these two separate things to work out and add together to get our change in mechanical energy. So change in kinetic energy, we have 1/2. We need the mass of both of the objects, so that's going to be 2,250. We need the final velocity, which is 20 meters per second squared. And we're going to subtract the initial velocity. And this is going to give us, let's see, we have 20 squared minus 30 squared. And we're going to divide that by 2 and multiply by 2250. and we're going to get minus 56250. There's my change in kinetic energy, and now we can do change in gravitational potential energy. So we need the mass again, so that's 2250. We need the gravitational constant, so that's given to us as 10, and now we need h. So h, what is h? Well, h is the change in height of the vehicle from where it started vertically upwards to where it ended. So if we consider the hill as 800 meters long, right, it's traveled up the hill 800 meters. At the point that the vehicle is at that height, we want to consider that. And because we know the angle, we were told this angle of inclination is sine inverse 0.08, which we're going to use sine now. Sine of sine inverse of 0.08 is just 0.08, okay? So what is the height? Well, if we look at the height, it is the opposite side of that triangle. So it's 800 sine inverse 0.08, which is the same as just saying 800 times 0.08. That gives us 64. Okay, so the height is 64. That gives us a change in gravitational potential energy of 1440000. Okay, and this is work done, so these are joules, by the way. Okay, now what we need to do is consider the work done. So the work done in this case is going to be the two forces that are acting in the direction of motion. We have the driving force and we have the friction forces. Okay, so work done is equal to force times distance. So how long are the forces acting for? They're acting for 800 meters, and this force here, this is the net force. Okay, the total work done. So the driving force is unknown. It's what we're trying to solve. It's acting in the direction of motion, and acting against the direction of motion is the friction force of 600 newtons. And both of these forces are acting for 800 meters. So we could consider their work done individually, or we can just take the net force and multiply it by the distance the force has moved. Okay, so once we've got all three of these things, we are finally ready to put them all together and solve for the driving force. So we said in the beginning, change in mechanical energy is equal to work done, which is change in kinetic energy. I mean, obviously you don't have to write this all out again. And let's put everything we've put in there. So we got minus 562,500 for change in kinetic energy. We got an increase in kinetic energy. And that was equal to driving force minus 600 times 800. And now we can just solve. Right, so we'll get 877,500. So we can divide both sides by 800. We'll get 8775 over 8 equal to... so the driving force is equal to, we're going to add 600. We're going to get 1696.875. So we need to round to three significant figures. So that one over there. So we will get 1,700 newtons as the driving force. Okay, so important to draw a diagram for yourself so you can see all the forces. You need to remember that when we are using the work energy principle, right, that we do not include this force as part of our work done, because we are already considering it as our change in gravitational potential energy. Okay, so we've pulled that force out and we've considered it rather as change in gravitational potential energy. Okay, in the second part of the equation, we are asked to find, well, it says after the vehicle reaches the top of the hill, the vehicle travels in a straight level road. The driving force of the engine is now 2,400 newtons and the resistances are unchanged. And they want us to find the acceleration of the system and the tension in the tow bar. So again, we've got to redraw our diagram because it's changed. We're now on a flat horizontal surface. I have marked the direction of motion. Right? I have marked the two different systems independently. So here we have the car, here we have the trailer. There's the resistance for the car, there's the resistance for the trailer, and there's the driving force. The driving force is only coming for the vehicle, it's not coming from the trailer. And then we have this tension, and using Newton's third law, for every reaction there's an equal and opposite reaction, that tension has to be the same. So the first thing we're going to do is we're going to consider the system as a whole, right? And that's going to allow us to find the acceleration. So using Newton's second law again, right, this is the net force, right? So what is the net force? Well, we have 2,400 newtons traveling in the direction of motion. That's the tension or the power from the car. And then we have minus 400 resistance on the car, minus 200 on the trailer. And we can use T in there, but they're just going to cancel each other out, so we won't add them. Okay, here we're considering the whole system, so we have to combine the mass again. And A. So we can very easily quickly just solve for A, 2,400 minus 400 minus 200, and divide that by 2250, and we're going to get 0.8 meters per second. Okay, and finally we need to consider the tension in the tow bar. Now we can consider either of the two systems independently to find the tow bar tension. I'll just do it from the trailer. So if we consider the trailer itself, again using Newton's second law, T is going in the direction of motion. The resistance is going against the direction of motion. The mass of the trailer is 750 newtons, and because the system is connected, the acceleration of the whole system must be the same as the individual components. So solving for T, we can take 750 times 0.8, and we can add 200. And that will give us 800 newtons. And just to show and demonstrate, we could have done this from the other part as well. So if we'd considered rather the forces acting on the car, we have 2,400 newtons going in the direction of motion. We have 400 newtons against, and also we have that tension against motion, the tension from the trailer. The mass of the vehicle is 1,500, and the acceleration of the whole system, and therefore the individual components, must be the same. So a little bit more working out here. We'll have to take T over to this side and this to that side. So we'll get 1,500, or we can rather say 2,400 minus 400 minus 1,500 times 0.8. And unsurprisingly should give us 800 newtons.